But because there's so much pressure, it's not like you get this big bubbling up out of it. What you get are these, as it's disturbed, is you get these bubbles that appear in the liquid, and you see the bubbles expand as it goes. But if the smaller bubble's here, the bigger bubble's here, then it's moving in that direction. You expose it to a magnetic field, you see how it curves, and you can pretty much start to narrow down, similar to one of the master set questions. You start to narrow down what kind of particle it is. And you get some poor grad student to do it. All right, so let's come up with our predictions. First, we're going to assume that special relativity is pure bunk. It's going to be traveling 2,000 meters at, oh, I didn't finish writing that down. Okay, they had it at 0.99 times the speed of light. So if beta is 0.99, I guess we don't need gamma yet. I know speed is equal to distance times time, or distance divided by time, as kids say today. And so I have 0.99 times 3 times 10 to the 8th meters per second is equal to 2,000 divided by however much time. So this is assuming there's special relativity does not exist. How much time would it take for the particle to make it down to the bottom of the mountain?
.734 times 10 to the negative 6.
Negative 6?
Yeah.
Seconds. So, I assume you got the same thing?
Yeah.
Okay. So roughly 4 half-lives. So let's figure out how many of those would survive. First, let's figure out how many half-lives that is. So this divided by 1 half-life of 1.56 times 10 to the negative 6 seconds. 4.3. So when I'm dealing in half-lives, I've got, let's see, I start out with some initial amount. So the number that should be there would be the initial amount times 1/2 to the t over the half-life. See if that makes sense. So when t is equal to the half-life, this is just 1/2 what we started with. When t is twice that, we're at a quarter. Okay, I'm good with this. So the prediction is, I think I said 516. 516 times 1/2 raised to the 4.3. Oh, actually, raised to the 4.3.
Uh, 26.
26. So special relativity does not work at all. Then at the bottom of the cliff, you should be getting 26 per hour. Obviously, they did not get 26. Otherwise, we would not be talking about this. Now, if special relativity is true, beta is 0.99, what is gamma?
Uh, 7.088.
So the idea is that from the muon's point of view, less time has passed than it has for the lab frame, where you're standing on the side watching this thing go by. So the proper time, gamma times the proper time, is equal to the lab frame. So the proper time would be t divided by gamma, or we had 6.734 microseconds divided by 7.088.
microseconds.
So if special relativity is making the claim that from the muon's point of view, just under 1 microsecond is passed. If that's the case, well, how many lifetimes is that?
Less than 1.
Yep. So we would do 0.950 microseconds divided by 1.56 microseconds to figure out how many half-lives it was.
.609.
And so the number that should be at the bottom
$338.32.
with confirmation? All right. The number that they got at the bottom, they were off by, I think, 1 off the special relativity. So 337, something like that. This was the first huge piece of evidence for special relativity having validity. At this point, you know, there's loads and loads. There have been several recreations of this experiment with more precise instrumentation, and they still keep getting confirmation after confirmation. So, physically, these muons, less time is passing for the muons than it is for the people who are standing on the side. Questions to hear before I actually talk about why I call this T sub P. This P stands for proper. There's proper time, and it's not called improper time, and just time. So the proper reference frame is the reference frame at rest. From the muon's point of view, the muons aren't moving at all. From the people on the side, the scientist's point of view, those muons are moving. So when we're looking at this, the muons, the rest frame in this situation is the muon's point of view. The next question, though, is, I'm going to give the muons sentience. Would the muons and the scientists agree on anything? Not a whole lot. They don't agree on the amount of time that happened. But they do agree on one thing. They agree on this 0.99, beta being 0.99. They just disagree on what's moving that fast. From the muon's point of view, what's moving at 0.99 times the speed of light?
Everything else.
Okay, the mountain in this case, yep. So if the muon is saying that this mountain is coming, or the base of the mountain is coming at them at 0.99 times the speed of light, how far does the mountain actually move? From the muon's point of view, how far is it moving?
2,000.
Well, pardon?
Oh, 2,000 meters.
Let's check that out. So I know that the distance is speed times time. From the muon's point of view, the speed is 0.99 times the speed of light, so times 3 times 10 to the 8th. And the time from the muon's point of view is 0.950 times 10 to the negative 6th seconds. That's meters per second. So this is from the muon's point of view. This is how fast the Earth is traveling, and this is how much time happens. Or the time, this is the time interval. So how far did the muon say the mountain has moved?
282 meters.
So they do not agree on the 2,000 meters. So this is the mu1 point of view. From the Earth point of view, the distance traveled, well, it better be 2,000. But it says that the mu1s are traveling at 0.99 times 3 times 10 to the 8th meters per second. And they're traveling for 6.734 times 10 to the negative 6 seconds. And it should be 2,000.
Yep.
What's the difference between these? From mathematically, what's the factor difference between the two?
10.
Pardon?
10.
Looking for more precise.
7.09.
Whoa! That's what we had right there. What a coincidence. So the relationship between distances also varies by this exact same factor. So we have time is equal to gamma times time proper. But what's the proper frame here? When you're talking about the length of the path, that's at rest relative to whom? I'm a scientist. I've got this experiment set up at the top of the mountain and the bottom of the mountain. I'm a muon. I'm traveling towards the ground. That length there, which of these is the proper length? And again, proper length, the proper anything is from the point of view of at rest.
So from Earth's point of view, since it's not moving?
Right. From the Earth's point of view, because the mountain's sitting right there, it's not moving at all. So that length, that distance right there is proper. So the length, the proper length is equal to gamma times the length. This is still the muon side over here. This TP and this L are both for the muon. This T and the LP are both for the Earth. But just recognize that the flip of what's actually considered proper. Questions to hear? Let's take it to the next step. Now we're making the claim that the speed of light does not matter the reference frame, that whoever's looking at it, the speed's the same. You're traveling near the speed of light, you're turning your headlights on, the light is going to leave your car at the speed of light. Even though you're traveling near it, it's still going to seem like the speed of light. Think about it, as you're driving down the interstate, and you're slowly gaining on the car in front of you. From your point of view, if your velocity is positive, what's the velocity of the car in front of you?
Negative.
Yeah, because even though I made a gesture like this, that you're getting close, you're coming up on them, from your point of view, you're not moving and that car is coming closer to you. From his point of view, your velocity is in the same direction as, well, the ground would say as well. So I have two twins. One twin is going to stay on Earth. The other twin is in a rocket ship. This is what we're about to talk about here, is known as the twin paradox. There's some distant planet over here, planet X. This rocket is going to go there and then come back. So from Earth's point of view, that rocket shoots out at, we'll just say 0.99 the speed of light, 0.99, theta is 0.99. So gamma was 7.09, I think. Oh, 8 something. So Earth's point of view. However, from the rocket's point of view, the rocket doesn't go anywhere. It sees the Earth travel over here and then back, and planet X travel there and back, and they're traveling at 0.99 times the speed of light. Is there any problem with these 2 points of view? Or will you accept these points of view?
Looks good to me.
All right. There's nothing wrong with these 2 points of view. That was not setting you up for the trick yet. Now we set you up. The person on the rocket is gone for a year. From his point of view, he's gone for 1 year. The time that passes on Earth is 7.09 years. But in this situation right here, the person on Earth is not moving. The rocket is moving. And from this point of view down here, the rocket's not moving, but the Earth is moving. So from one point of view, it should be that, let's see, so from the point of view of, so this would be like the muon equivalent and the non-muon equivalent. But over here, it seems like then the Earth should have aged 1 year. And the person on the rocket should have aged 7.9 years. They're just flips of the same situation. In one situation, the Earth moved, and the other situation, the rocket moved. But when the rocket gets back to Earth, only one of these can be true. It's not like they split into 2 different people. What is the difference then between these 2 situations? Because the 2 points of view are both valid, but there's obviously a difference between the 2. This is what happens. The person in the rocket ages a year, the people on Earth age 7.09 years. What's different in the 2 scenarios? Louder, please.
The Earth is not actually moving off of other than rotation.
Oh, let's not worry about the Earth rotating, going around the sun or anything like that.
So that's the stable one?
So, but why is, so you're saying Earth's not moving, but why is that more valid why is that more valid than saying the rocket's not moving?
Is it because it's bigger? Like more mass, is mass have effect here, or?
The mass of the Earth is not an issue.
Is it reference point?
Meaning?
Things around you, like people around you, things around you.
Oh, the fact that other people observe you, therefore that's a quantum physics thing. No, not an issue here.
Is it relevant that the Earth is not moving because the speed of the rocket, which is causing it to age less?
Well, all right. So let's sort of examine that. The analogy.
Could it be that the person that came up with the year was on Earth?
He never left. So I got 2 vehicles here. According to the ground, this vehicle is traveling at, we'll just say 30 meters per second, and this vehicle is traveling at 25 meters per second. So from the ground point of view, from the policeman who's standing there with a radar gun, this is what he gets. call that A and B. From A's point of view, so A's point of view, A is not moving at all. How fast is B moving?
5 meters per second towards them.
Okay. From B's point of view, B is not moving. How fast is, what is A's velocity?
Same thing, 5 towards.
This is the type of situation we're working with here. They are all valid ways of looking at it. If you ever make this argument to the police officer of, you say I was going 100 miles an hour, but according to the car in front of me, I was only going 60. Let me know how that goes. But these are all three valid points of view. These are both valid points of view. There's not, you can't make a reference to any of these not moving. I mean, even if you make the argument the ground's not moving, well, the ground's on the earth and the earth is moving around the sun and the sun is going around the center of the Milky Way and the Milky Way is moving out. And I mean, there's a whole lot of movement going on. So we established a reference here. You typically, the police only care about the ground as the reference, to my knowledge. But here, but it's not necessary, but it is valid to also make the argument that A is not moving, the ground is moving that way at 30 meters per second, and car B is moving towards A at 5 meters per second. That is completely valid from a physics point of view. But there's something physically different about what happens to the rocket and what happens to the Earth. And that is the key for why both of these situations, one of these situations is not the same as the other one, besides point of view.
Does it have anything to do with numbers?
I think you could easily make that argument, but what are we thinking?
I mean, would it be gravitate, or would
Say it
it
again?
be gravity?